was that
we have a current carrying wire, like the one that's shown here in brown, and that's a cylinder. The cylinder is this current carrying wire, and you can tell that it's a current carrying wire with a current flowing out of the page, and that's indicated by the dot at the end of the cylinder. This is a current carrying wire with current flowing towards us out of the page. And according to the right-hand rule, if the current is flowing in the direction of my thumb, it's conventional current that is, then the magnetic field should be curling, I suppose you would say counterclockwise, if this conductor is viewed from the end. And so at a distance I've labeled it as R1, you would have a magnetic field of a certain intensity that might follow the contour of this red dotted line. And at a distance R2 away from the current carrying conductor, right over here, you would find that there's a contour that would have an equal magnetic field intensity, and it would be oriented also counterclockwise around the current carrying conductor. Now, as you get further away from the conductor, or as you increase the current or decrease the current, the magnetic field is going to change. The magnetic field intensity is going to change inversely proportionally to the distance you are away from the conductor. That is, the further you get away from the conductor, the weaker the magnetic field intensity is going to be. And the stronger the current is, or the higher the current flow rate is in your conductor, the stronger the magnetic field intensity could be. So there's a few control variables that we might have here for changing the magnetic field intensity around a current carrying conductor. Now, if I want to talk about a current carrying conductor in terms of proportionality, we could say the magnetic field intensity is proportional to current over distance. But some people would like to talk about a constant that corrects for this proportionality issue. And if you wanted to find a constant, we could call it a K constant. We could say, well, magnetic field intensity divided by the ratio current over distance away from a conductor does give you a constant value. And the constant, we could call it some sort of a magnetic constant. You know, a K stands for constant if you're Pahonetic or phonetic. And we could call it K subscript M, but more commonly people talk about it as being not a K constant on its own, but a combination of constants. Now the 2 pi pops up because of some integration around a circle, but we're not going to worry too much about the idea of integration or the fact that it's a circle just now. This K constant could be rewritten as a composite of a few constants, mu naught over 2 pi. And mu naught is a description of how well magnetic fields permeate into space, or how permeable a vacuum is in terms of allowing magnetic fields to be set up within that vacuum. So the idea of how well a magnetic field can permeate into a space is described by this mu constant. And so for a vacuum, oh, there's an announcement. For a vacuum, this constant would be 4 pi times 10 to the power of negative 7 Teslas of magnetic field per meter per, sorry, not per meter per amp, Tesla meters per amp. And of course the 2 pi stays on the bottom if we were calculating it as K. If we were just expressing it as mu naught, then it would be 4 pi times 10 to the power of negative 7 Tesla meters per amp. But if we needed to introduce the K value, we'd have to divide by 2 pi. Now, the only reason I bring up the K value is because we have a textbook that seems to be in love with the K value, whereas much of the rest of the world is more interested in talking about it in terms of the magnetic permeability of space. That's in terms of mu naught. So I want to bring up the mu naught just because it's useful elsewhere. So 2 times 10 to the power of negative 7 times, or sorry, Tesla meters per amp would be the K value, but more people would express it in terms of mu naught. Now, if I want to introduce that constant into the magnetic field equation, rather than having magnetic field as proportional to current over radius, here's the current over radius, mu naught over 2 pi would be introduced in this way. And the reason I wanted to keep the 2 pi is because you can see right in this formula, 2 pi r is a circumference. We know that. And we know that this is a magnetic field whose intensity is being spread out around a circumference, just like ripples on a pond. The magnetic field intensity is spreading out over ever-increasing circumferences. And then the strength is also determined by the current that's being flowed through that conductor. Now, if I wanted to do some calculations with this, sure, why not? We can say, look, if you want to find the magnetic field intensity a certain distance, let's say 2 centimeters, that is
2 meters away from a conductor, and you want to flow a certain current through this conductor, or allow a certain current flow through this conductor, let's say 4.5 amps, you could measure the current flow with a multimeter set to the amperage setting. And you could measure the distance away from a conductor, let's say with a ruler or something simple like that, and we could get these as measurable values. And by taking these measurable values, we could calculate the magnetic field intensity. Now, there are devices that can directly measure magnetic field intensity, but this is a nice way to calculate the theoretical value of the magnetic field intensity near a current-carrying wire, or nearby the pathway of any current that's flowing, but it oftentimes is flowing inside of a wire. Now, I've shown the cancellations here already, but if we substitute in our values as well as the mu value being 4 pi times 10 to the power of -7 Tesla meters per amp, you see pretty quickly what gets canceled out. The 4 in the mu constant cancels out partially with the 2 pi in the denominator, so the pi is gone, and the 4 divided by 2 reduces down to being just a 2, or simplifies to being a 2. 2 times 10 to the power of -7 Tesla meters per amp times 4.5 amps divided by 0.02. Now, I know that this is a 2 here and this is a 2 here, so there's going to be some cancellation there. And I know that if the 2's are going to cancel out, this is going to end up being 4.5 times 10 to the power of something. Now, you can put in the calculations, and what you're going to find is that it's 4.5 times 10 to the power of 5 Tesla. If you want to make sure that the units are canceling out, I see a meters in the numerator, I see a meters down here, I see an amps in the numerator, and an amps down here, all canceling out. And lo and behold, as always, we have units that are nice and clean, that work out as they should. Magnetic field intensity of 4.5 times 10 to the power of -5 Tesla is what will be found 2 centimeters away from a 4.5 amp current.